Well, good morning, good afternoon, good evening, wherever you're tuning in from, and welcome to SETI Live. My name is Simon Steele. I'm the Deputy Director of the Carl Sagan Center for Research here in Mountain View, California. And a very special guest today, Michael Lamb, a SETI Institute researcher. And we're going to be talking about some exciting results from Michael's research. And he is part of NANOGrav, and NANOGrav stands for the North American Nanohertz Observatory for Gravitational Waves. I had to read that off the page. So welcome, Michael. It's wonderful to see you and meet you. Say a little bit about what NANOGrav is and how you got involved in this exciting project.
Absolutely. Yeah, nice to speak with you too. So I'll break it down using the collaboration's name. So North America, that's easy. We're primarily made of scientists across North America, a bunch of other countries as well, but the US, Canada, and we use North American telescopes. We use the Green Bank Telescope in West Virginia, the Arecibo Observatory while it was still operational, Very Large Array in New Mexico, and now CHIME, which is a radio telescope in British Columbia, Canada. Okay, so that's the easy part. And gravitational waves, so I'm going to go to the end of the name. Those are ripples in space-time that are permeating through us right now, through everything. And they change the distances between objects in space-time ever so slightly. And they're caused by things like very, very massive compact objects spinning around, swirling around each other. And gravitational waves were predicted by Einstein and were only first observed a few years ago by the LIGO and Virgo collaborations. And there's been lots of exciting news about black holes that have been merging and neutron stars that have been merging. And so then the last part is the Nanohertz Observatory. So what does that mean? 1 nanohertz, so that's a frequency. That's how it's a rate at which something is oscillating. And it's not a very usual unit. 1 nanohertz is the frequency corresponding to a period of about 1/30, or a period of about 30 years. So that is LIGO and Virgo are these gravitational wave detectors, and they try to measure very, very high frequencies, hertz to kilohertz. So things spinning around and orbiting less than a fraction of a second around each other. And for us, we're measuring objects that are spinning around each other with months and years and decade periods long. So very, very, very different experiment. So that's what NANOGrav is. Hopefully I explained that okay. And how I got involved is I've always wanted to be an astronomer, and I always want to do that. And then during college, I talked to one of my professors, and I said, neutron stars are crazy. I want to get involved in research. And he guided me and said, oh, you should apply to these summer internships. And I got involved in Pulsar research. And I didn't know it at the time that this was the exact research. This was NANOGrav research because it had just started a few years earlier. And I loved it. I thought it was great. And I went to graduate school, and I wanted to keep working in Pulsars. And yeah, that's how I got involved and kept going all the way.
Okay, great. Thank you. And just a reminder, do let us know where you're tuning in from. I see some of you have already done that. Monica from the Canary Islands jumped in first, but let us know where you're viewing from. And if you do have any questions, because I'm going to turn the questions over to everyone who's tuned in about halfway through the show, do let us know if you have any questions, and we'll try and get to as many as we can. Michael, I just want to go back a bit further. Ripples in space-time predicted by Einstein. This is a weird property of empty space, isn't it? And can you say a little bit more of that? And especially in gravitational waves, we all have sort of views of what waves are, whether they're crashing on the beach or sound waves or light waves. How similar or how different are gravitational waves to the waves we know and love?
Right. Yeah, it's a great question. And it's really not intuitive because nothing that Einstein said was very, very intuitive. The ripples in space-time. Well, let's start with what space-time is. It's the everything that makes up the universe. So there's 3 dimensions of space and 1 dimension of time, and that's how we describe where anything is and when anything is in the universe. So I'm sitting here, and there's 3 dimensions that describe where I am this way, and this way, and then I can check my watch, and that's what time it is. And so that's how we understand. And Einstein said that all of these are connected. And his theory of gravity, which is extremely well tested, says that there's relationships between all of these, and where masses and energies are in the universe. And masses and energies actually warp that space-time, and that's not an intuitive thing at all. So if you have lots and lots of mass compact together, then it can actually change, it folds space-time. And maybe many of you have seen one of these demonstrations where you go to some place and you roll a coin around kind of this well-looking thing, and the coin spins around and then goes to the bottom. Or you can imagine taking a sheet. You have this giant sheet and you put a ball in it and it sags in the middle. That's kind of a crude representation of how a mass will curve space-time. So the little fabric of the sheet is changing, and that's kind of what's happening here. But it doesn't actually require things in space-time, and that's what's weird. So when you have waves crashing along the shore, what's happening there? That's water moving and actually hitting a shore. Or sound waves are the air molecules in this room. They're vibrating as I'm talking, and they're bouncing back and forth. But this is a property of space-time itself, that you can have these waves rippling through, and they're generated somewhere. So they're generated by objects, but once they're generated, they just kind of travel through the universe. And the net effect of the waves, the gravitational waves, is that the distances between objects will change ever so slightly. So, if you and me are sitting in the same room, then as gravitational waves are passing, even if we try to be as still as possible, that the distances between us are changing ever so slightly.
Because the size of space is changing.
Yeah, exactly. The literal, if this is the X direction, the X, Y, and Z, X is actually changing ever so slightly. That's right. And these have been measured many times by, again, LIGO and Virgo, and I think we have lots of evidence for that now for us.
This idea of space having structure, because it comes up a lot in astronomy, it doesn't come up in many other places. The universe is expanding, and we think about space stretching. Where gravitational lensing is another manifestation, isn't it? And some of the latest JWST images of these distant galaxy clusters show how space can be distorted, and then light has to travel through distorted space. But now we've actually got ripples emanating. How fast do these waves travel compared to light?
They travel at the speed of light, pretty much, yeah. So they can be slowed down, just like light can be slowed down certain ways, but so they're traveling at the speed of light. I prefer to call it the speed of information, just because the light misnomer makes it feel like it's only light that can travel at that speed.
Okay, thank you. And these gravitational waves, as you say, they've been around for a while. I think was it back in the 70s where the binary pulsars, the Hulse-Taylor pulsars, were the first. That was the first ever detection or proof that there was gravitational energy, I believe.
Yeah, that's right. And I'm a little biased because I'm a pulsar astronomer at heart, and so the broader astronomical community, they often refer to that as an indirect detection of gravitational waves. Because what was done there is you observe 2 pulsars, and they're very, very compact objects, so they're warping space a lot. They're orbiting around each other, and as those are emitting gravitational waves, those gravitational waves take a little bit of energy out of that system. And then you take some energy out of the system, the orbits start to shrink. So as they're orbiting around, the size of the orbit gets smaller and smaller and smaller and smaller. That means that the period of the orbit is starting to get faster and faster and faster and faster. And so that was measured, and it exactly matched the prediction by gravitation, by general relativity. And so that was, I think, excellent evidence that gravitational waves existed. It was a perfect prediction. And unfortunately,
but they didn't see the waves.
but that's the problem, is that, and so I'm a scientist, so I think, well, we want to build up evidence towards understanding something. And I think nobody believes that there is another explanation. You see the exact match, but it wasn't actually seeing the waves. And I do concede that point. So I understand why people will call it indirect evidence. But I agree. I think in the 70s was when gravitational waves were really first evidenced by observations. Absolutely.
Yeah. Maybe we should go back now to talk about the other things that have just come up in the conversation, which is pulsars and the role that these compact objects play. I mean, these are the universe's most accurate timepieces, aren't they? Can you say a little bit more about why pulsars are important in this sense?
Absolutely. So pulsars themselves are rapidly spinning neutron stars. So what's a neutron star? When a very massive star undergoes a supernova explosion, its its massive core, and so it sheds off a lot of material, and the massive core ends up gaining what we call angular momentum. So the big star is slowly spinning, but then as that blows off, the core is left that's going to be rapidly spinning. And it's going to be a very dense environment and very stably spinning environment, because you take this very massive compact ball, you start it spinning, and it's hard to get it to stop spinning because it's just got all of that angular momentum. And so that's what a pulsar is. A pulsar is a neutron star at the center where there are these beams of light coming off of both axes. Actually, I have a pen here. So it's rotating around, and every time the beam passes you, we see a pulse. So it's there. I like to call them cosmic lighthouses, because every time a lighthouse beam passes you, you see it, and then you don't see it. You see it, you don't see it. So the pulsars are not pulsating. It's just that we see them as these pulses. And it's really a miracle that we have these objects in the universe, because they're so accurate. They're as accurate and precise as our best atomic clocks here on the Earth, but they're in space. And so they in themselves are really cool objects to study, besides using them for tools for gravitational waves. And we like to study them because, for example, they're the densest objects that we have in the universe besides the singularities of black holes. And so, for example, if we understand and make measurements of the neutron stars themselves, we can understand what physics is doing at nuclear densities. That is, the densities of the nucleus of an actual atom. And we can't do that here on the Earth because we can't pile nuclei together to that density. So it's the only place in the universe where we can do this kind of science, and we can't do it in an Earth-based lab. There's lots of other science cases, because these are incredibly extreme objects that we can study only here. There's no lab that we will ever be able to build on the Earth. So that's why I got involved in them. I think their neutron stars are crazy. I love working on them.
Yeah.
And then on top of that, because they are such precise clocks, now you have an experimental tool with which to do other very cool science at the same time. You're making the same measurements, but you're just extracting different amounts of science. So you can use these to test gravity in different ways. Where might Einstein have gone wrong in his experiments? We haven't found that, or in his theory. We haven't found it yet in our experiments, but these are some of the strongest tests that we can do. And then on top of that, one of the motivating things that has pushed the science along the way is you can also use them to observe gravitational waves. And so that's why everybody is, really excited to engage with these objects and observe them.
Right. We'll get back to how that actually happened in a second. Just somebody claims they're from Mars. Welcome. It's good to get a signal that far. Usually can't get the next town over. California, Ohio, Michigan, Sydney, Australia, Pennsylvania, UK, Syria. Welcome. Bulgaria, Virginia, Santiago, Chile. And I was going to read one more, and I can't find another. Northern Illinois. We'll take that. Thank you so much, and thank you. Some of the questions are coming in. So rotating pulsars, neutron stars colliding in themselves have produced gravitational waves that have been detected by LIGO, and these are high frequency gravitational waves from before. But now, of course, as you say, we're using pulsars not through their ability to collide with each other, but their timing mechanism to look at basically how space is stretching and squeezing with these very long period gravitational waves. Can you say a little bit more about the experiment and the results you got?
Yeah, sure. Yeah, so we took almost 70 of the best pulsars. So every pulsar is really good, but some of them are better They're better clocks. And we wanted to take the very best of them. And what do I mean by best? I mean, these are objects where pulses will be emitted. They'll travel through thousands of light years through our galaxy. They'll arrive at the Earth, and I can predict when they will arrive at my telescope to well within 1 microsecond. And those are like our worst of that sample. Some of the best ones we can predict to within 100 nanoseconds. And that's the precision and accuracy that you need to do this kind of experiment. And thankfully, the universe has provided us with these objects. So what is our detector? We have radio telescopes here on the Earth, the ones that I've mentioned, and many others around the world used by other international partners. They're observing these the radio emission from these pulsars. We're doing that as well. And we are observing almost 70 of these objects spread across the galaxy. So take a good fraction of the size of the galaxy and you're putting all of these pulsars down. That makes up our detector. So our detector is made up of these different pulsars. And so as gravitational waves are passing through the entire Milky Way galaxy, that's what we're measuring. Analogously, what LIGO and Virgo, when you build a ground-based detector here on the Earth, you're measuring how gravitational waves are passing through the Earth, right? Or some small fraction of the Earth. And for us, we're measuring how the gravitational waves are passing through a good chunk of the size of the galaxy. And so that's what you need in order to build this, what we call a pulsar timing array. That's the kind of detector. It's an array of pulsars where you time them. You time them to very high precision in order to make these kinds of measurements.
And that brings a question as to what's doing this, because, you know, again, we with the LIGO and Virgo detectors, there's an understanding of what's producing those short frequency or high frequency rather gravitational waves, and these are colliding neutron stars. They're black stellar mass black holes, small black holes that are potentially coalescing, and those are causing the intense ripples. So what's the theory behind this you know, this stuff that's just sort of lapping around, you know, using a nautical wave analogy, lapping around the galaxy and the universe?
Absolutely, yeah. So I'll start with what is probably what we think the source is. And then I'll get into some other interpretations as well. And the reason I say probably think it is actually we cannot at this point in time definitively say, yes, the gravitational waves are coming from this source. We have an understanding of other things in the universe because there's other astronomers doing lots of other science. So we think it is probably from a certain source class. And that source class is from supermassive black holes in binaries. And we know that at the centers of every galaxy is a supermassive black hole. The Milky Way has a supermassive black hole in the center. That is a very lightweight supermassive black hole. That's 4 million times the mass of the sun. So that's what I mean by lightweight. And the ones we're observing are on the 10 billion times the mass of the sun side of things. So you take a galaxy with a very, very massive black hole in the center. You take another galaxy with a very, very massive, supermassive black hole in the center. And we see lots of observations of galaxies merging all over the universe. Hubble shows lots of that. JWST shows lots of that. So we know that galaxies merge. So if the galaxies merge, then you would sort of expect that the supermassive black holes in the center should also merge. Mm-hmm. But there has actually been no evidence of that so far. And there actually isn't evidence of that even now, because we cannot yet definitively say that our gravitational waves are coming from those sources. Again, it is entirely consistent with our understanding of how black holes should merge. And we're using our measurements, even if we aren't definitively saying that's where they're from, to say, okay, well, let's assume that they're from supermassive black hole binaries, because there's lots of supermassive black holes in the universe and galaxies merge. What can we understand from that science? And we can say, well, we now understand, if we make that assumption, that those black holes should either be more massive, on the more massive side of where theoretical models predict, or there should be more of them on the more plentiful side of where theoretical models predict. And we understand something about what the environments are like in those galaxies as they're merging. Is there a lot of gas? Are there a lot of stars near the black holes, or are there not a lot of gas and not a lot of stars? Turns out that's probably more towards the former, where there's a lot of interactions with the material in the galaxy. It's not like many of the stellar mass black holes that have merged, where they kind of have merged in isolation, and you only see gravitational waves and you don't see anything electromagnetically. That's really exciting for us, because if there is a lot of stuff going around, we expect to see them electromagnetically. And so in the coming years, we really hope to say, here is a supermassive black hole in binary in gravitational waves and in electromagnetic waves, and we're going to be able to really constrain things and understand those properties. So that's what is probably happening. That's what we've been joking is the mundane explanation are 10 billion supermassive or 10 million solar mass black holes colliding across the universe.
That's a wonderfully mundane.
Yeah,
we're talking about that's mundane. Give us some
exactly.
of the weird possibilities as well.
Exactly. Yeah. So, yeah, if that's not weird enough, the weird, not even weird possibilities. We know that, for example, at the very early instance of the universe, right after the Big Bang, was a moment that's called inflation. And that's when the universe grew greatly in size, many, many, many orders of magnitude. And during inflation, we know that gravitational waves were produced. And so it is possible that there are early universe mechanisms at play here that are causing the gravitational waves that we are observing right now. Again, we can't even definitively say that's the case either. It's got to, we're not sensitive yet enough to definitively say one or the other. We test lots of different models. If it's not from this early moment of inflation, it could be from what's called early phase transitions in the universe. So you can imagine that when you, for example, take water and you freeze it, you're doing what's called a phase transition. You're going from a liquid into a solid. And when you do that, when you make that solid, the ice cracks a little bit. And the same is actually true in the reverse direction, right? As the ice cracks, you're going to get all this cracking. The same is actually true, or can be true, for space-time itself. And in that cracking, you can produce gravitational waves. There's a lot of other things that can be producing it. So, for example, dark matter, we know dark matter exists, but if there's a certain class of dark matter, because we don't really understand dark matter at all, that can produce a signal in our measurements as well. So there's lots of explanations out there for what this could be, and really only time is going to tell as we get more sensitivity, and we do that by observing our pulsars for longer, by observing more pulsars as well. We'll get better sensitivity, and we'll be able to say, yes, some of this is from supermassive black holes. Some of this is from other things as well. We don't really expect it to just be an either or game, right? Whatever exists in the universe, all of those gravitational waves are encoded in our data.
Yeah, excellent. It'd be nice if it does start constraining models on dark matter, definitely, moving forward. Yeah,
absolutely.
So I got a couple of questions here. One from Wayne, and he asks, how fast do these waves deteriorate? I suppose we can interpret that by deterioration or sort of losing their sort of amplitude as they spread out. Maybe that gives us an idea of if they are sort of coalescing supermassive black holes. Maybe what's the sort of range you think they have to be within for you actually to be detecting them? If that,
of course. Absolutely, that's a great question. So if there's nothing else in space, gravitational waves will travel forever. They'll just travel forever, and they'll move at the speed of light, and that's all we'll have. But if there's stuff in space, just like with electromagnetic waves, I said before that will actually slow the waves down a little bit. And as they interact, as gravitational waves will interact with stuff, other matter, they will actually lose a little bit of energy because there's just some energy there. And so there was work that was done, for example, a couple of years ago that said, okay, if the intergalactic medium, that is the space between galaxies, if it's very dense, for example, and we don't think it's that dense, but if it has a certain density, there's enough stuff throughout it, gravitational waves will lose energy over as they're traveling, and then might never actually reach us, because if these gravitational waves are produced really far away and then they get damped, by the time they get here, we'll actually never measure anything. Now, that's a very that's a statement of this intergalactic medium being very, very, very dense. And if it's less dense, then there's less damping. And if it's really, really not that dense, then there's not a lot of damping. And so our measurements, however, so we have evidence for gravitational waves. Our measurements are suggesting that if they're coming from supermassive black holes, they must be coming from hundreds to thousands of hundreds of millions of light years or thousands of millions of light years away from us. It's all of these galaxies out to an incredibly vast distance. So there really isn't a lot of damping, or there's effectively no damping at all. And we're seeing these mergers from, again, hundreds of millions, thousands of millions of light years away. Really good fraction of the size of the universe.
Mm-hmm. Nice. A quick digression from Les, wondering how many pulsars there are that we can't detect because their axis is not tilted our way. Is there an estimate for how many pulsars are there in the galaxy, I suppose?
So right now, the number we know of is in the sort of 3,000 range. It's a little bit above 3,000. That's how many we have measured. You can then say, okay, we know where all these pulsars are. Then you can try to make an estimate of how many pulsars are actually out there. That's a little bit harder, because part of the problem is you need to know what that axis. So if they're rotating like this, they're rotating exactly on axis to you, then you actually don't see a pulse. Ooh, let me try to do that as well. You don't see a pulse at all, because as I'm rotating this around, there's nothing actually pulsing. It's not it's always on your line of sight. Now that's very specific orientation towards you. We don't actually know the exact distribution of how the beams are offset from the rotation axis. So if they're very, very, very offset, that actually tells you a different answer in how many there are that should be out there versus if they're less offset or not. So the number that we think are in the and I should say the number of neutron stars that we think, I'm probably going to be a little bit wrong, but I'm going to say something like 10 to 100 million of them in the galaxy. Okay. Right. Compare that with the 100 billion normal stars that there are. So it's a small fraction. And if I'm off by an order of magnitude, somebody don't blame the messenger. But it's something in that range. It is a wide range though, so we're not exactly sure. Okay, and then the other part of the question was,
I think that was it.
Okay.
Yeah, no, that's good. That's good.
Okay.
I could add this one. What's the closest? There's two questions that combining from Sky and also from, I think it was Steve. Closest pulsar, and is it possible to detect pulsars in other galaxies?
Yeah. So the closest pulsar, it's funny. We've been preparing for the answer of what's the farthest one that we know of. The closest one to us is a few hundred light years away from us. We have pretty good. I don't remember the exact number, but it's a couple hundred light years away from us. And then, can we detect them in other galaxies? The answer is yes, but we haven't yet detected any radio pulsars. There have been a few measurements of X-ray and I believe gamma ray pulsars. So that's on the much higher energy range where we can't really do the precision timing. So they're less interesting from the perspective of trying to use them as this astrophysical clock, but we still know that they're there. There are some radio pulsars that are known in the Magellanic Clouds. These are these dwarf galaxies that are orbiting around the Milky Way. Those are known. But if you go to, say, Andromeda, which is the closest big galaxy to us, we have not yet seen any radio pulsars there.
Okay. So pulsars are visible throughout the entire electromagnetic spectrum, but it's the radio that gives you the type beaming that gives you the timing.
Exactly.
Okay, excellent. Question from Adriana. Just read it out, and it's on screen for you. Frequency is about period, but what about amplitude of these waves? How do they affect our space-time? So how are we being stretched and squeezed, and by how much as these waves pass through us?
Right, and the answer is very little. So I'm going to start with what LIGO measured, because what LIGO measured was way smaller than us, and then I'm going to tell you how big our gravitational waves are, how strong they are. So we quantify how strong gravitational waves are by a quantity that's called the strain. And the strain is how much is some distance changing, the fractional change in the distance. And so if a distance changes by this much, that's about half. So that's a strain of about 0.5. I'm changing it from here to half the size and back. Now that's a very extreme change. LIGO detected a strain the first time of around 10 to the minus 21. Okay, so that's 0.00000, and you go 21 over, and you get a 1 at the end. That's an incredibly tiny number. What does that mean? That means you take their detector, which is 4 kilometers long, and so then you have to do the math, and you say, okay, 4 kilometers, what is 10 to the minus 21 of 4 kilometers? And you end up getting, so you get something like 10 to the minus 18 meters. You get a change of distance to within the width of a proton. Mm-hmm. That's how much of a change there is. It's incredibly tiny. So 4 kilometers long, and the distance is changing by less than the width of a proton. So nothing that you have to worry about. Okay, that's what LIGO and Virgo have observed so far. We, on the low frequency end, we have observed amplitudes, strains, 1 million times larger than that. However, so okay, you go up 1 million, that's 10 to the minus 15. So that's still an incredibly tiny number that nobody really has to worry. You don't have to worry about your height changing by gravitational waves. But what does that mean in sort of practical terms? If you work it out for our experiment, you say, how long are we observing for, and what is the light travel time, and you take 10 to the minus 15 in there. It means that between us and pulsars, which are thousands of light years away, then space is changing by maybe a few tens to a few hundreds of meters, and that's it. And a good rule of thumb, so I'm going to change my units here, is that light takes about 1 nanosecond to travel 1 foot, so a third of a meter. 1 foot, a third of a meter. So 100 nanosecond precision, that means that's 100 feet, or about 30-ish meters. That's how much space is changing. Space-time is changing between us and a pulsar over the duration of our experiment. And that's why we need the precision we need, is actually because those are the amplitudes, these strains that we're measuring. So thousands of light years being changed by a few tens of meters, is not really something that we need to worry about here on the Earth, but is apparently, is measurable.
Which is amazing. I mean, 10 to the minus 15 meter. That's the diameter of an atomic nucleus, not even an atom.
Exactly.
So exactly. This is extraordinarily impossible to imagine, as is the distance of space and everything. Question, and I can't. I'm not going to pronounce your name, but Zapfan's fan. Can you? Thank you. Can gravitational waves be lensed? That is, are you focusing as these waves pass through, say, a galaxy cluster?
Yeah, just like with electromagnetic waves, gravitational waves can also be lensed. There were some suggestions, so some people have done theoretical work where they thought we might actually be able to detect individual sources of gravitational waves from extremely far away if they were lensed towards us. Mm-hmm. So you could get some measurements from the very, very early universe. If we happen to have very favorable geometry, that is, you happen to have a cluster in between, and you happen to have that binary that's right there. And the lensing, just like with electromagnetic light, you can get a magnification factor. So you get an increase in the amplitude. So that was a really, that is, I think, still a very exciting prospect, that if the universe if we're kind of lucky, that we might be able to do that. Not guaranteed. It's not as common as with electromagnetic signals, where we see gravitational lensing all the time. That's just because the number of sources out there are not as many. Like there's way more stars out there than there are supermassive black hole binaries. So it's a little bit of a numbers game, but they absolutely can be lensed.
Right. Okay. Thank you, everybody, for the questions coming in. I just one last one to talk about the future. NANOGrav has been going for 15 years. It's obviously not time now to wrap things up and lock the door behind you. What is next for the project? Or maybe what's your aspirations for where to take this project now?
Yeah, absolutely. So we already, our 15-year data set ended in 2020. It's taken us that long to analyze and really make sure that everything, we understood our statistics and really understood what it was that we were saying about our evidence. Just taken a very, very long time. So we already have several more years of data that we have collected, because it's 2023. We haven't stopped observing. We've kept observing over that time. And so that forms the next of our data sets. We're really interested in combining data sets with collaborations around the world, because they all see similar hints to what we're seeing at various levels of significance. And so you think to combine the data, that you can pull out even more significance, even more sensitivity to other sources and things like that. So that's on the very, very near term, is doing this data combination. And for NANOGrav is pooling resources to say, okay, let's also look at our next data set. We're really excited to crack it open and work on it. It takes a long time. The data combination is hard, because telescopes around the world are doing all different things, and you have to pool it together in some common way. And pulsar timing is just a hard endeavor in general. Then going into the near future, the mid future into the far future, I think what we want to do is, like I said, we want to keep timing for longer. We want to time more pulsars, and we've done a lot of work to say how many really good pulsars are there that we can observe. And we haven't found even half of them, we think. We think that there are many, many more out there, based on our understanding of surveys that have been done, that we can go and observe and add to our pulsar timing array. So we can really grow the array and make it just way more powerful. That will give us much, much more sensitivity. We're working to propose to build new telescopes. So one of the concepts that I'm sort of involved in, I'd like to get a little bit more involved in, is called the DSA 2000. And that would provide us absolutely fantastic sensitivity. It would give collaboration like NANOGrav a lot of time on the telescope to go and observe all of those pulsars. And so that's, kind of my dream of the next 5 to 10 years, is that we'll have new telescopes coming online. And that's just the telescopes that we're using. There are other telescopes that are proposed or are coming online in the future for radio astronomy. They will be looking at pulsars all over the place. They will be extremely sensitive telescopes. So you get more data, observe more pulsars, build the array up, go look for new and exciting stuff. I want to see what the low frequency gravitational wave universe looks like. That's where we're going.
Wonderful. So this is just the start, just the beginning.
This is just the start. Yep.
Yes, excellent. Thank you, Michael. This is amazing stuff. Very, very exciting. Thank you, everybody, for tuning in. Thank you for your questions. Thank you for telling us where you are from. We do these weekly, roughly. So tune in to the SETI Institute website, seti.org, to find out what's happening next, and sign up for our mailing list, so you'll get much more information about the research going on at the SETI Institute and events like this coming up in future. A reminder that the SETI Institute is a non-profit organization, so we do rely on donations from members of the public. So have a think about that, and the donation banner has come up instantly down the bottom. So thank you again, Michael. Thank you, everybody, and we will see you again soon. Take care.